So we are going to be recording, as I said. What I'm going to do is I'm going to be turning my camera off in a second. Let me make this screen larger. What's the talk going to be about, or what's this presentation going to be about? It's going to be about EvaM tools. This is basically an R package and a web-based app that allows you or gives you access to all of the state-of-the-art methods for what used to be called cancer progression models, but are now called, or we try to refer to them as evolutionary accumulation. Let me start my chronometer. Evolutionary accumulation models. Probably the main place where you want to go for the code and to download Docker images and whatnot is this GitHub page, but it's fairly easy to find. So we provide this as an R package that you can install, as a Shiny web app that you can access from our servers, and these are also provided as Docker containers. Since the whole application has a bunch of dependencies, it might be just simpler and more straightforward to download the Docker containers. And we've been adding recently, actually in the last couple of days, a few additional methods. So what is the main functionality we provide? We allow you to upload your own data and do inference on them. We allow you to construct synthetic data and do inference from this synthetic data. And we also allow you to simulate data from models and do inference from them. This might be a little bit abstract. It should be clearer in a few minutes. And then this is not available from the web app, but it's available from the R package. You can do simulation, or you can simulate the actual models themselves and then go to step 3. So since what cancer progression models and evolutionary accumulation models might not be familiar to everybody, let me start with a quick outline of what they are. And this is the basic motivation for them. So this idea of cancer as an evolutionary process where not all orders of accumulation of mutations are equally likely, basically because we might have epistatic interactions, so that mutating gene B might lead to a lethal outcome unless you have mutated gene A previously. So this is the basic sort of setup. Let's start referring to the figure on the right. We are basically going to have a collection of patients. Every patient is going to be measured only once. So this is why we have scratched this. Every patient is measured only one. We don't have like sequential data, but we have multiple patients. Each one, as I said, measured just once. I'm not going to get here in this talk about whether we assume strong selection weak mutation, so that we have basically monotypic populations, or we have possibly populations composed of different clones. This is an interesting separate debate. I'm not going to get into that here today. The main point is we have a collection of patients. Everyone has been measured once. And what does the data structure look like? So we have a matrix of subjects, of patients by events, genes. We assume, or these data are either binary or have been binarized. We have multiple subjects, as I said, at hopefully different stages. We don't have information about the stage of any subject. We are going to assume in most of these methods that once an event has been gained, it cannot be lost. And this data, basically what every patient provides, is just like the tumor genotype, the mutational profile of every one of these subjects. Before we continue, it's very important to understand that we are not doing phylogenetic inference. So this is a typical example of phylogenetic setup. We have a collection of samples from the same individual, say multi-regional sampling, and then we try to understand the phylogenetic relationships of those samples. This is not what we are doing. What we are doing is what we have here on the right. We have a collection of individual samples of different individuals, and we are trying to use those different individuals to understand what are the restrictions or or dependencies in this in the accumulation of these events. So we are basically assuming that in this cross-sectional data, the different individuals are replicated evolutionary experiments, and these evolutionary experiments have been conducted under, say, the same genetic constraints if we are dealing with genetic events or mutations. So let's see a collection of the different models or types of progression patterns we can see. Would be probably the simplest one. This is a linear dependency structure. So suppose we have a collection of subjects where about 500 of them have no mutation whatsoever. We are going to call them the wild type. Around 250 have only gene A mutated. About 150 have both A and B, etc. This suggests that we have a linear pattern where we first need to accumulate A. Only once we have A, we can gain B. That gives us the genotype AB, etc. So this is just possibly the simplest linear accumulation model. We can make these models much richer. This was one of the first, it was actually the first computational model for these types of problems. On the left, we use a tree to specify the restrictions in how mutations can be accumulated. This tree is telling us that gaining A and gaining B are independent of each other because none of them depend on the other, but gaining C requires A. An arrow denotes direct dependency. From this set of restrictions, we can derive the set of possible genotypes we can observe, either A or B, or both A and B, or both A and C, or the three of them together. And when we fit this model, we estimate these conditional probabilities, and that gives us basically, or from that, we can recover what the expected frequencies of the different genotypes are. An elaboration of this model, this is a tree, an elaboration of this model are disjunctive Bayesian networks where an event, say C, can depend on two or more parents. And this model actually allows us to use two different types of dependencies. We can have a conjunctive dependency, an AND operation. So to gain C, we require both A and B. And we can have disjunctive relationships where to gain C, we require just either one of them or both. So we can have C and A, C and B, and C, A, and B. But C would not be observable on its own. Both oncogenetic trees and OncoBN are what are called untime models. This gives us the probability of observing the different genotypes at the time of observation. But other models use continuous time formulation. One of the first one was the conjunctive Bayesian networks. It looks very similar to the previous one. These are conjunctions, these are AND, but this is a continuous time model. The virtue or the nice thing about these continuous time models is that they result in they give us the rate of transition between genotypes as a continuous time Markov chain. And we can use this to obtain different derived quantities, like the probability of observing different genotypes at different times. A further elaboration of this model are HESBCN. We can think of this of HESBCN as CBN, the previous method, but with additional types of dependencies. Instead of just having only AND operations, we can have also OR operations, and we can have XOR, exclusive OR. The exclusive OR here would mean that we can observe E with A, and we can observe E with B, but we cannot observe A, B, and E simultaneously because of this XOR operation between A and B as parents of E. This also gives us a continuous time Markov chain models, with this being the rates of transition between states. All of these models I have talked about are deterministic dependencies models. We require something to happen for something to happen afterwards. But there are also stochastic dependencies models, where what we are going to be modeling here are not deterministic dependencies, but just facilitating or inhibiting dependencies. This is a very busy slide, but the key thing to focus here is in this row over here. This tells us, well, how are we going to model the rate of transition between from one genotype to another? So how are we going to model the rate of transition from genotype AB to genotype ABC? And that's going to be modeled as the product of two different quantities. One is the spontaneous rate of gaining C, and the other are the facilitating or inhibiting effects that the already existing genotypes or mutations have on these new mutations. So this would be the inhibiting or facilitating effect that A has on C, and the inhibiting or facilitating effect that B has on C. Now, as you can see, these are pairwise interactions. They need not be symmetrical, so the facilitating or inhibiting effect of A on C need not be the same as C on A. And this pairwise interaction is what MHN, this method, Mutual Hazard Networks, is modeling. Hypertraps allows a much richer set of models. So we can have the L2, the pairwise interactions, but we can also have just models with just main effects. So just the spontaneous activation of a gene, or we can have three-way interactions, four-way interactions, and we can have completely unrestricted models. Completely unrestricted models are models that are just directly modeling the transitions between states in this hypercube of transitions. Okay, so how have these models been used? They have been used to describe tumor progression. They have been used to try to model the relationship between progression and survival. And they have been used to try to estimate predictability or make conditional predictions of what's the next genotype going to be, given on the genotype that has happened before, etc. But these models have been used outside of cancer. They have been used quite a lot to model mutation acquisition in HIV. And they have also been used on completely different problems that have basically no genetics underneath, or no explicit genetics, like malaria progression in children, just modeling symptoms of malaria accumulation. Okay, so let's move on to EvaM tools. But before I actually go to the webpage, this I already said. What sort of problems can we address with EvaM tools? Basically, we can analyze our data and get inference. So we have a data set. What do the different methods say? That would be a fairly straightforward use of this package. But there are other things we can do. We can try to get an understanding of what these methods are really inferring. So EvaM tools is going to help us do that. How? We can answer questions like, well, what if I had this data set? What if I increase the sample size? What if I remove a particular genotype? What are the different methods going to tell us? And I think a much more interesting use case is actually this one, to get an intuitive idea of what the different methods mean in terms of what the data would look like under different models. It's not always obvious what the different models imply. So with EvaM tools, we can explore this fairly easily in a graphical user interface. We can also answer questions about, well, what if my models have been, what if my data have been generated under, say, an stochastic dependencies model, and I analyze it with a deterministic dependencies model, or the other way around? Or what is really the implication of having exclusive ORs, etc. So let's move on to the actual web interface. Let me go over here. So let me hide over that, and let me hide this thing over here. So if you go to our servers, this is the URL. You land over here. This is the main page. This is the entry page. This is basically where you also have a very simple user's manual of how you can use this app, what the results are, how to enter the data, what are the default options. An important thing to note here are it's additional documentation, so you can click on it and it will open this PDF with a long tutorial, a 45-page tutorial. This PDF doesn't include the two newest methods we have just incorporated, but it should give you a fairly good idea of the sort of things you can do and a step-by-step procedure. So let's go on to that. So this is what you find when you open EvaM Tools. And let's look on the left. You can upload data, you can modify genotype frequencies manually, or you can generate data from either DAGs or one of the stochastic dependencies models. And you are going to also see, if you have already run some examples, a list of the examples you have already run. Since I was running a few ones before we started, they are shown over here. So let's go on to the upload file, just to show you what sort of things we can do. So I'm going to upload, this is something that has been uploaded like a few minutes ago. Let me upload a data set here. So this is a data CSV file I already have. I'm going to upload the same one. I'm going to open it. It tells me, well, that name is already in use. So I'm going to change this name. I'm going to call it BRCA-EX over here. I'm going to rename my data. So that's already done. Once I upload the data, I can analyze it directly, but I can also modify the data if I want by changing some entries. Say, let's pretend I want to increase the number of wild-type genotypes to 100. I type 100, Control Enter, and as you can see, the data have been modified immediately. And I could now run this example. Before running it, let me enable some methods that are not clicking here, and let me disable a few other ones that tend to be longer. So once I do this, I'm going to be running 3 particular methods, 2 with deterministic dependencies, these 2 over here, 1 of them with stochastic dependencies. I could be changing other settings here. We don't need to, but you can change them if you want. Probably you don't want to change the number of cores, since this is running on our servers. You're not paying anything for this, so you can leave that at 8. And there are other options for some of these methods. You can play around with them. Some of them are explained on the additional documentation. We don't need to change them right now, so let's just click on Run. And when I click on Run, we are going to see a tiny image, a tiny message here on the bottom right telling us it's running. So it says running, and it eventually produces the output. Okay, so it should be over here. It needs to do a few rearrangements to find the optimal sizes of the output. So we have here the output for the 3 methods we ask for. These are the sets of restrictions these methods identified. The actual DAG is very similar between these 2 in this particular case. MHN doesn't return deterministic dependencies. We said that already. This is giving us the matrix of pairwise dependencies between the different methods. What we are shown next are the transition probabilities between the different genotypes according to these models. These are transition probabilities. We can show genotypes. We can actually ask for a different type of representation, which is just give me what genes are being gained at each state. We can change the number of relevant paths that are being shown. So from most relevant paths to less relevant paths. Okay, so just these are going to lead to busier figures. Instead of transition probabilities, we can ask for transition rates. Not all methods produce transition rates. In particular, these 2 methods are untimed methods. So we are not going to be showing seeing anything here. We see transition rates for MHN. We are also being given that as in tabular output. We could ask for, well, what are the models telling me for the predicted genotype frequencies? You can see the histograms here. You can also see a tabular representation for the different genotypes and also the original data. You can also order these tables. Just focus on whatever you might be interested. Okay, let's go back. As you can see, actually, the analysis we just conducted is being saved here. These are things I ran right before the tutorial to have them over here. Let's go back and let's see a different way of playing around with the data. We can enter genotype frequencies manually. So this just brings me here where nothing is being shown. I can change the number of genes I play around with. I could change the I could change the name of the gene. So maybe I don't want something to be called A, but I want to I want to have something like BRCA. Just use these genes and let's enter a few counts, okay? If I type Control Enter, that's at this genotype, that's going to be wild type. You see the histogram. Let's have 12 for BRCA, and let's have 34. We can add genotype, okay? And we could ask now this to run the analysis. And let me change this like synthetic for synthetic data. I change it over here and I click run, and it's going to produce. Sometimes you can see these warning messages. They are innocuous. This is a bug we haven't been able to solve in the last 2 years, but never mind. It's innocuous, nothing happens. And you can see the output here. This is not a particularly interesting data set. Let's do something that's much more interesting, which would be, we're not going to run it here, but you might be asking yourself, well, what if instead of having 112 wild type, what if I had only one? Would the models change? Well, you just type the number, change the counts. You would probably want to rename the name of the data, and you would just click or run again so that you can compare the output. Let's go on to using directed acyclic graphs. This screen is going to allow us to do a bunch of different things. We can first use or modify already preloaded. This is done by default. These are always preloaded examples with different numbers of genes and different numbers of structures. So we have a fork with 3 genes, a fork with 4 genes. You can see that the DAG is changing here on the right. We have a linear model. We have a model with AND, a model with OR, and a model that includes XOR, and then a model like the one I showed before that includes ANDs, ORs, and XORs. Now let's stick to this example. Now, this is a basic model where I could change the entry values for the lambdas, the dependencies. So let's do that. Let's put here, instead of 0.7, let's put here 1.2. And as soon as I do that and I start playing around, I get data, synthetic data being generated under this model. Okay. We have around 100 observations here, and that's actually the case. I could, instead of generating 100, I could ask for, well, don't give me 100, give me 200. And I would say, click generate data. But as you have seen before, as soon as I start playing with things over here, the values are being modified dynamically on that figure. But I can also modify the structure of the figure here. So this is, as you can see here, an XOR relationship. This is shown in red. Well, what if I wanted to make that an OR? I can type OR. I only need to modify one of them because the program is smart enough to know that all the dependencies for a descendant need to be the same. So I just did that. You notice, you can see how this changed to yellow. I actually use this quite a bit to just produce figures for papers or talks. Well, but I can actually modify the structure of the DAG. So let's say, well, let's make E independent of B. So I'm going to remove an A, an H, E, B, and I'm going to do this, remove H. I remove the H. A new data set was automatically generated from here. But let's do something which is even more interesting, which is add a new edge. For I'm going to add an edge from E to D, and I'm going to say, okay, so I just changed the graph. Well, what if I want this to be an XOR? That's a piece of cake. We just go here and type XOR, and then type enter. Okay, that changed the model. And again, I can change the rates. We have seen this already. Okay. Now, some of you might have noticed that I have here the model. Well, this is a continuous time model that allows this type of relationships. What if I said, no, I actually want an untime model? Well, I could try doing this, but it's going to tell me you cannot do that because there are several reasons. One is under the OncoBN model, the parameters need to be bounded between 0 and 1. Oh, okay, so let's change that. Let's go over here. Let's just write 0.7, and then there is a 2 over here. Let's write 0.9, and there is a 1 point here over here. Let's go write 0.6. Now, okay, let's try to do that operation again. And it says, no, you still cannot do that because the OncoBN model does not allow for XOR relationships. Okay, fair enough. So we are going to try to set an OR here. And then let's try to do it, to turn it into an OncoBN. And it says, no, you cannot still do that because under the OncoBN model, all the relationships need to be of the same kind for a particular model. This is a restriction compared to the HES-BCN model. Okay, never mind. I can still fix that by doing that. And now I got perfectly fine. And I can do that. Okay, now I can get and as you can see, actually, the simulated data change because even if we have apparently the same numbers for the parameters, the actual empirical implications for the type of data that are being generated differ. And I could, of course, run this as we have done before. Let me finish showing different types of model generations with MHM. But before I do that, let me show something else. We might want to generate the observational data with some genotyping error, and we can just include that over here. Okay, if I do that, generate data, you can see that the histogram changes. Of course, if I use a very large genotyping error, then I get basically, I can blur the signal. Let me go to a different type of modification of the models. This is a stochastic dependencies model. The default is just a matrix filled with zeros. I can again change the number of genes. I could change the names of these genes. I'm not going to do it now. I can change the number of samples. Let me put this in 0. And I can generate data. One of the things that happens with the MHM model is that it might not be intuitive what this model really means. So let's start playing with that. This is the matrix of dependencies. I'm going to change the diagonal for some genes. So I want to increase the rate of acquisition of gene A. Let's turn that into a rather large number. And you can see that the histogram of what's happening of the observed data is changing quite a bit. Well, let's add now a positive relationship between A and B, so that when you have A, increasing or gaining B is increased. Let's use a large rate, and let's see what's going to happen here on the histogram. As you can see now, we get a lot of ABs. We basically get no A's on their own, because as soon as we get B is being produced. Let's decrease that number a little bit, and then that set of relationship is going to change. We could have a negative interaction between A and B and D, sorry, so that whenever you gain E, gaining D is inhibited, and that's going to change a few things here, etc. Okay, so you can play around with this type of. There is no reason for this to have these numbers. We can have this to be 3, so that when you gain C, and then let's make C a little bit more present, etc. We can start playing around with this and try to see what the empirical implications of these models are. We can reset everything here. Go back to the standard field. So let's look now at some of the results we have run, and let me show you a few examples with some longer running data. This is a particular example I ran before. I ran a few additional methods. In particular, one we added recently, which is hypertraps. This is a fairly busy picture. You do not need to show all the models at the same time if you want, so I can click and make 2 of them disappear. It takes a few seconds. It readjusts the screen, and then we are only going to be shown these 3 methods we asked for. As before, we can ask for transition probabilities, transition rates, predicted genotype frequencies, etc. But let me focus on a particular method, hypertraps. Hypertraps, when you ask for this method, you also get some additional output for hypertraps, which is going to depend on the particular model of hypertraps you ask for. One of the important things to keep in mind is hypertraps is sampling-based method. You want to look at the trace of the likelihood. Based on this trace, it seems that the model hasn't really stabilized itself, so we would probably want to run this longer. This is actually what I did in this output over here. This is the trace of the likelihood for a hypertraps model that was run for longer. It's also it's actually a different hypertraps model because this allows for 3-way interactions, so we are being shown a different type of plot for the relationships, or the inhibiting or facilitating relationships between genes. And let me, I think I'm running over time. There is, well, we could continue showing things here, like modifying the output of the graphs here for the types of, for the transition probabilities, etc. But I think I will probably stop for now. I had a bunch of additional examples pre-computed here, where I was running. Yeah, let me show this just real quick. So I loaded a different data set. It's a data set that has a larger number of genes. It's also a classical data set from the literature. It's provided with the package. And this data set contains a larger number of genes, or a larger number of events. I have already preloaded it, but if I were to try to run this data set, let's do that real quick with just some of the fastest methods available. Notice what's going to happen. This is okay. It just tells you something. It says, beware, you are analyzing data with 7 or more genes. This can take longer than usual. Fine, I am going to dismiss it because in this particular case, for this method, that's fairly fast, and you can get this output. So when you play around with the web interface, you are going to be shown examples that sometimes warn you of things like this can take longer, or as you saw before, sometimes precludes you from conducting certain operations because you want to manipulate a DAG in a way that's actually not possible. Well, it's going to tell you, it's not going to crash, it's just going to tell you, you need to do something before you are able to accomplish this step. And I think I'll stop for now and just move to to questions if there are questions. And I think I just need to shut up and wait for questions, right?
Yes, of course.
Okay. So if there are any questions, I'll be happy to address them. Let me move over here. Let's hide this. So any questions? Anything else you would like me to demonstrate or show? Hide this thing over here. Would you rather me show or play around with, say, modification of the DAX a little bit more, or we have, I think, what, like 10 minutes left? Is that correct?
Yes.
Okay, so anybody could interrupt me if they wanted, right? So if there are no questions right now, let me do a few additional things showing you the interface. I'm going to hide. Let me first go over some of the results, and let's look later at modification of the DAX. So this thing, just to give some feeling for the things we are being shown here in this particular model. This is a model which I think has like 7 or 8 genes. We have run this model with 3 of the fastest methods available here, 2 untime models, 1 stochastic dependencies model. Again, this is showing the DAG or the tree of restrictions. This is only a tree, so any node can only depend on one parent. That's oncogenetic trees. That's the way it works. OncoVN, however, allows for joint or multiple dependencies. You can see like this particular gene over here. Let's make this larger. This particular gene over here depends on 3 parent nodes. This is going to depend with an OR relationship. OncoVN model can have models where there are OR relationships or models where there are AND relationships, but it cannot have models where you have both of them at the same time. Where do you choose that? In the advanced options. If you go to the advanced options, let me make the font larger. If you go to the advanced options, when you go to OncoVN options, you are told it shows that the default model is using disjunctive, but I could run that model with conjunctive relationships. Okay, let's see what models have we clicked. Let's use this with OV2 OV and okay, I rename the data and then I run it. We can dismiss this because these methods are fairly fast. And now we are going to see that, well, there are no AND relationships here, but had there been multiple dependencies, they would have been shown with an AND, right? So, okay, something else to see over here. Let me go to the other screen here. Let's go to some of the pre-run examples. Let's see if it's over here. Okay. Okay. This method is a method that can allow for dependencies both with AND and XOR and OR in the same model. But in this particular case, it gave me none of those relationships. It just gave me a star relationship. That's the best model it was able to find. A few additional things I want to show you. Since we have a few seconds. Just this is sometimes disconcerting for some people. So let's say I want to change the different names. This is not going to be allowed here in a model that has already generated, or in a data set that has already generated data. If you try to click on use different names, it's going to tell you you cannot do that when you have already generated data, because that would be confusing very quickly. If you want to do that, you need to reset the data and then use the different names. Now, what if I want to use a gene that has that starts with a Z? If I use that, it apparently tells you it's over here, so we can just modify you, okay? And now you are going to see that we are playing around with with our new model. C is probably not a gene name we want to use, but maybe we want to use P10 and P53 over here. So we can just use that if we want and generate data for that. Okay, I think I'm running over time, right?
Yeah.
So okay, all right, perfect.
Indeed.
So thank you very much. I should just stop the recording and that's it, right? And close the session.
Yeah.
Is this correct? Okay, perfect. Well, thank you very much. Thank you very much to everyone for attending. Bye.
Thank you.
Bye-bye.
Bye bye, Ramon.